What is rate of reaction? It is also called a velocity of reaction or speed of the chemical reaction. On the basis of the velocity, we have classified all the reactions into three types. The fast reactions, very fast reactions, very slow reactions, and the reactions of moderate rate. The fast reactions means they will be completed, reaction will be completed in few seconds, within that 1 or 2 seconds or few seconds. Examples, as you know, the ionic reactions. In inorganic chemistry, most of the reactions are ionic reactions. They proceed at faster rate. And the slow reaction, very slow reactions that we have seen in the nature, it is the corrosion of metals, maybe the iron, bronze, copper, and the weathering of granite, that is a stone, granite or limestone. This weathering and corrosion of metal, it is all because of the rusting or corrosion. It is all because of presence of air pollutants in the atmospheric air and the action of water or water vapor. So these reactions are very slow. So it takes many years to complete. They will take many years to complete the reaction. They are the very slow reactions. And what are the reactions of moderate rate? They will be completed in few minutes or in few hours or in a day or two. Those reactions are reactions of moderate rate. Chemical kinetics mainly concerned about these chemical reactions which proceed at moderate rate. So now let us understand what is the definition for the rate of a reaction. One equation is given, that is showing a chemical change, chemical reaction in a generalized form. It is a stoichiometric equation, balanced equation. And here the mathematics plays an important role. As you know, the differential calculus and integral calculus finds very important application in the study of chemistry and in the study of physics as well. This is the application of what is differential calculus and integration in this case. Look at that, the mathematical equation. This is the equation for a chemical reaction. This is the equation for definition of the rate of this reaction. This is a stoichiometric chemical equation. The rate of this reaction is defined in 4 ways because there are 4 substances. These are reactants. A is a reactant, B is a reactant, C and D are the products. There are 4 different substances. The rate of this reaction can be represented either in terms of the A or B or C or D, like this. I'll tell you later in detail what is this. Rate of this reaction in terms of the concentration of A, or rate of this reaction in terms of the concentration of B. Here, rate of the same reaction in terms of concentration of C, in terms of concentration of D. So this equation, if you take this equation, rate of a reaction is equal to minus 1 by A into change in the concentration of A in the interval of time, in this change of time. Delta says change in the concentration, this delta says change in this time. how do you find this change in concentration, change in time? Very important. It is the one we need to measure. As you know, I said chemical change means A and B changing into C and D. This number of molecules of A and B, that is disappear in the just in a single step of reaction shown by stoichiometry. Disappearance of that will result in the appearance of C and D, number of molecules of C and D. We cannot, that is a chemical reaction. Any chemical reaction usually is invisible. You cannot see the reaction first of all, because molecules are small, so small, and that also we can't see the change in the concentration. Not observable, it is direct observation, it is direct, not visible directly. But we can sense the concentration change of any substance, either reactant or product, in the reacting system. How? Using what is that? Equipments. That is proper, what is that? Experimental setup. Equipments, a proper equipment now. That is, we are designing a set of experiment is designed. That is, merely designing, man-made design. Is a design only for that reaction. It may be different for different reactions. Usually design now. So whenever whenever we make a study on this reaction, we need to see what are the equipments we need. It is set up. And what is that? Is that designing of this to see that or to measure the concentration of reactant or product in that reacting system. We all need that experimental setup, very important. Experimentation and experimental equipment setup, designing for that particular reaction, very important. So after that, we can able to monitor the concentration of either any reactant or product. So it is said either this or this. So with this experimental setup, we need to, what is that? You have to find these values and these values. How you can find out? Experiment, reacting system, using that system or setup, let us measure. So if you take the rate of reaction in terms of what is the concentration of A, we measure the concentration of this reactant at different times. That is, it is keep changing the concentration. Concentration of A is changing with time. You have to measure, you have to take the values, you have to record the values of concentration of A at different times. So we get a set of data, concentration values and times corresponding, and put them into graph, a graphical representation. Those values, we get a graph like this, curve, not a straight line. This is a curve, represents variation of concentration of the reactant A with respect to time. See that it decreases with time. This is a way of decreasing concentration of A reactant with time. So once you get a curve like this, we can calculate the rate of reaction. So mathematics, simple mathematics, what is that? graph, and we have to find out this value, delta A, delta T. From this graph you can find out. So this graph says that here any point on the graph says that some concentration value and corresponding time. Take any 2 points on the curve. This is one point, other point. And to this point the corresponding concentration is A2. For this corresponding concentration value is A1. From the graph only you can read it. After writing this one, after you get this graph, corresponding time, that is T2 and T1, 2 to 1, 1, different times. So this is take the difference, you just according these values, take the difference in values, you get change in concentration, delta A, and take the difference in these two values, change in time, delta T. So put them into this, what is that ratio? Change in concentration, change in time. it gives the rate of disappearance of A, rate of change of concentration of A from this graph in this interval, and the rate of reaction is directly related to the magnitude of this value but inversely related to the coefficient of these molecules, because these molecules once for all disappear in one step, that is 1 by A, that is directly to this and inversely to this. So rate of reaction depends mainly two factors on the basis of this chemical equation and the concentration values, rate of change of concentration values. So we get this value from the graph and we get this value from this stoichiometric equation, and minus for this minus represents the concentration decreases with time, because concentration of reactant decreases with time. That is why minus 1. Either A or B, same equation in terms of B. Here same equation in terms of C. Here concentration of C increases with time, concentration of B increases with time. That is same definition, but here coefficient is 1 by C, coefficient is 1 by D, plus represents this concentration increases with time, minus represents concentration decreases with time. For reactants it takes minus sign, for products it takes plus. So you can take any one of the equation, either this equation or this equation, depending on what concentration you measure. If you measure the concentration of A, it is a graph you get. We get this. Use this equation, calculate RA. Suppose we monitor the concentration of C with time by the experiment. We can use this. What is that? Set of values into the graph. We get a graph like this. Look at the graph difference. This is a curve for a reactant, curve for the product. Concentration of the product increases with time. That is a curve like this. Different slopes. There is slope variation. Slope variation. Same graph. In the same way, do the calculation. Take any 2 points on the curve. These are the concentration values. These are the corresponding time values. Take the difference in values. Higher, lower, higher, lower. This difference in value is this. This difference in value is this. And take the value from this and calculate the rate of reaction. So this is the rate of reaction, is the average rate of reaction or mean rate of reaction. Why? Rate of reaction is never be a uniform. It is not a constant at all. Rate of reaction is keep changing, varying at all time, because this equation says that rate of reaction is a concentration dependent. These are the reactants. This concentration decreases, rate also decreases. So with the time, rate of reaction, speed of reaction keep decreasing time. So that is why I am talking about this rate of reaction. Here, what we have calculated the rate of reaction, it is a mean value between these two times, because we have rate of reaction at this point, we have at this point one more rate of reaction, at this point one more rate of, there are different rate of reactions. Between these two, we are taking mean. It is a mean rate of reaction or average rate of reaction between these two intervals or between these two concentration terms. That is why it is called as average rate of reaction. That is a mathematical definition for what is that? That is an integral. That is an integration. Now the differentiation is very important, special importance. Here Ri, it is Ra. Ra means instantaneous rate of reaction. What does it mean? So it is the same graph, same set of values. Experiment we have performed using, we are monitoring the concentration of A, the same graph, or monitoring the concentration of C, the same graph like this. Using this graph, what is that? We need what is that? Instantaneous rate of reaction. What does it mean? I said no. Every point on the curve, every point here, different concentration, different time. At every point, rate is different. So rate of reaction at that instant is called as instantaneous rate of reaction. This mathematics finds application very important. At any point in the curve, we can calculate the rate of reaction. It is called instantaneous rate of reaction. What does it mean? It is a differential calculus. Delta, this in place of delta, it can be dA dt. How do you find dA dt? Again, a graph. Differential calculation. The same graph. If you want to find the rate of reaction at this instant, this is some time, that is some interval of time, that is at this instant or at this concentration. We have every point has some concentration, some time, that is after this interval of time. So if you take any point of this, you have to draw a tangent to the curve at this point to calculate dA by dt. When you draw the tangent, now draw two straight lines so that they can meet at a point, vertically at any point like this. And after drawing the tangent, you have to calculate what is the slope of this tangent. The slope gives this dA by dt. There are two ways of calculating. In the graph now, it's not. You can see what is the measure the length of this. This is the length. Measure the length of this. This length by this length gives the ratio dA by dt. Or if you are able to measure the what is that angle between this tangent and this vertical line, it is a straight line, that is theta. Tan theta means opposite by adjacent. Same thing as either measure theta and take tan theta, that gives the slope of this tangent, or take the ratio, measure this value, take the ratio. Either way gives the slope of this tangent. The slope of the tangent is called as rate of change of A with time. This is how we can measure these values from the graph. Then calculate what is the rate of reaction, that is for this equation, what is 1 by A minus. Same thing as what is that. So it is for this A or it is for this C. Example for this. So any point, I take this point, draw the tangent to the curve at this point, find the slope of this tangent. This is a way of finding this. There are two lines we can meet vertically at any point, this like this, at a point, and find theta from this. Tan theta or dC by dt. Calculating dC by dt or theta gives tan theta. Slope of this tangent. The slope of the tangent is dC by dt. Substitute into this equation. Calculate Ri using C. This plus for product, minus for reactant. So what the rate of reaction we get either from here to here, that is the rate of reaction at that instant. This is the rate of reaction at this instant. And similarly you can calculate the rate of the same reaction at any instant. You have to take this point, draw a tangent, find this slope. Or this point, this time, at this instant, draw a tangent at this point, find this slope. So like that. So at any point, at any instant, using this concept, we can find the rate of reaction. It is the instantaneous rate of reaction. These values are infinitesimally small values. It is dA and dt. What do you get from this now? Comparatively, you see the magnitude of these values. These values are what is recognizable, finite values. These values are very small, infinitesimally small values. That is a differential calculus, differentiation of this. So that is why it is instantaneous rate of reaction. It is average rate of reaction. Once, if you have a set of what is that experimental values from the experimental setup, we have what is designed for a particular reaction. We can go for either average rate of reaction in that particular interval time, or rate of reaction at any instant can be calculated using this graph. So this is the rate of reaction I am talking about of any reaction in general like this. There are two reactants or one reactant or three reactants. The same concept is experimental determination of rate of reaction. The most important one. That finds application of experimental setup and mathematical concept, differentiation and integration. This next is that one more important rate constant of the reaction. For example, this is the what is that stoichiometric equation. This is a rate equation. What I have written already. Rate of reaction in general is equal to it is rate constant of the reaction into concentration. Concentration exponent of this concentration exponent of this. I need to define the rate constant. This rate here in terms of this, where to find the rate of reaction we are using this, either this or this or this. So rate constant means when you put this is equal to 1, this is equal to 1. Concentration. What is concentration? Molar. Molarity is a concentration. Molar. Molar means mole per dm cube. So many moles in 1 liter. So many moles in 1 dm cube liter both are same. That is concentration. If it is 1 molar, if it is 1 molar. So 1 to the 4 of anything is 1. The 1 to the 4 of anything is 1. When this becomes 1 and 1, R equals K. That is a specific rate constant. K means rate constant. K means rate of reaction only. But we need to specify rate of reaction when concentration of all the reactants equals 1 unit concentration, 1 molar. That is rate constant. So rate constant means rate of that reaction when concentration of all the reactants are found to have only 1 molar. Rate constant. So for that rate constant, let us write the unit as well. Unit means using the same equation. Let us see what is the unit of this rate constant. Rewrite the equation. R divided by this. Rate of reaction means unit for rate of reaction means molar per second. Constant. What is the rate means? Concentration change with time. Concentration is mole. Change in concentration also molar. How many moles changed? What is the molarity change in that time? That is called molarity. Change in the concentration. Molarity in that time per second. Mole per second. And this is a concentration term. It is a molarity. Molarity of B. M. That is symbol. M stands for unit. Power X. Simplify this. Here base mark, same exponents are different. X plus y is equal to n. So m, that is the numerator, denominator. M is here. Take it to numerator. This becomes minus. Becomes sum. Exponent becomes minus 1. Plus 1 already is 1. This becomes minus n. Then m to the 4 of 1 minus n. It carries 1. Not shown here. 1 minus n into s to the 4 of minus. Unit of rate constant. Unit of rate constant. So this unit of rate constant, you look at that molarity, that is time. It is also carrying what is that value of n. So value means order of reaction. So unit of rate constant is depending on the order of reaction. For different orders, we have different units of rate constant. Let us see later. For different order of reactions, what are the units for rate constants? So with this, let us finish it off.